morning, everybody. I am Dr. S.S. Naidu, Assistant Professor in Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss about a very important topic in probability and statistics. That is, we are doing very interesting sums on correlation. First of all, let us see what is meant by correlation. See, whenever two variables x and y are either increasing or decreasing according to some proportion, then what relation that they are maintaining? Suppose the correlation between them is significantly high or low. All these things we can depict and we can represent using our statistical methods. So, correlation is a very important topic in probability, especially in statistics. So, there are so many methods are there. Especially two methods are there. One is rank correlation, and second one is Spearman's rank correlation. So, in these two correlations, we find the correlation among the given variables x and y, and how those variables significantly vary from one and another. Using that correlation constant, we can find whether the given data is reliable or not. So, if that correlation is significantly high, then we can judge whether that given data is reliable. Like that, finding correlation, we can find so many other benefits from the data. And see, this correlation coefficient concept is very much useful in analyzing data. So it is useful in aeronautics and so many other business-oriented programs and other business solutions. In so many fields, we can use this concept correlation. So, a correlation coefficient of 1 means that for every positive increase in one variable, there is a positive increase of a fixed proportion in the other. First one I told, for a fixed proportion. For example, shoe sizes go up in almost perfect correlation with foot length. See, normally they vary from for elders from 6, 7, 8, 9, 10 maximum. See, according to the foot size, the shoe size is designed so that it is designed not only according to its length, according to its breadth also, according to its height also. So, see, in all the three dimensions, it has to be developed, it has to be designed. So, that is called proportion. So, your shoe sizes go up in almost perfect correlation with foot length. That is called correlation. It gives a perfect relation. And one more point what we have to learn is a correlation coefficient of -1 means that for every positive increase in one variable, there is a negative decrease of a fixed proportion in the other proportion. They are varying proportionally. The amount of gas in a tank decreases in almost perfect correlation with the speed. As speed increases, proportionally it vacates. 0 means that for every increase, there is not a positive or negative increase. The two just aren't related. So, the random variable of a standard normal distribution is known as the standard score or a Z score. Z score, we have already previously we have discussed about this. The Z score can be defined as the using the formula Z is equal to x minus mu by sigma, where x is random variable, mu is mean, and sigma is standard deviation. Using these values, we convert that matter into our Z score. Then we use normal distribution, and using normal distribution tables. Normal distribution is also known as Gaussian distribution. So using normal distribution table or Gaussian distribution table, we use Z score values and we convert them into Z score values and we simplify them. So this normal or Gaussian distribution is a very common continuous, it is a common continuous probability distribution. Normal distribution or Gaussian distribution is a continuous probability distribution. Now let us see types of correlation formulae. There are several types of correlation coefficient formulae. One of the most commonly used formulae is Carl Pearson's correlation coefficient formulae. Among the first significant one is Carl Pearson coefficient of correlation. Coefficient of correlation. If we taking a basic stats class, that is the one we probably use, R is equal to, this is the standardized formula, R is equal to N into sigma xy minus sigma x into sigma y whole divided by square root of N into sigma x square minus sigma x whole square into N into sigma y square minus sigma y whole square. So this is the rank correlation formula. The rank correlation coefficient R is equal to N into sigma xy minus sigma x into sigma y whole divided by N into sigma x square minus sigma x whole square into N into sigma y square minus sigma y whole square. So using this, whatever data is given there, first of all, we have to write those values x, y, xy, and below that in column sigma xy we have to find, like that in rows sigma x we have to find, like that sigma y we have to find, like that sigma y square values we have to find, and sigma y square also we have to find. So sigma x whole square we have to find, sigma y whole square we have to find. A big tabular form we have to write there, and using that table, finding with the help of those values, we have to substitute all those values in this formula, and we will find the value of R, rank correlation. So here, if we analyze rank correlation, positive correlation, it goes in a significant way in a quadrant 1 like this. Here R is equal to 0.4. Is it positive correlation? We show like this. And rarely any one point touches this line of regression, and other points they will be very closer to this and they won't touch this. That is the significance of positive correlation. Like that, we can show graphs for negative correlation and other correlations also. Here, correlation coefficient formulae are used to find how strong a relationship is between data. That is the very, very important point. Here, correlation coefficient formulae are used to find how strong a relationship is between data. If the rank correlation coefficient is high, much strong relationship is there in the data. If that result is 0, no relationship at all. If relationship, if that R value is very small, very weak relationship is there, like that we will analyze. The formula written a value between -1 and +1. So 1 indicates a strong positive relationship. -1 indicates a strong negative relationship. A result of 0 indicates no relationship at all. So these we have to keep it in mind. So these are the graphs for that. Suppose here we are taking, in first graph we are taking a relation from x and y values. Here R is 0 means it is a perfect straight line, and all the values are above and below, and they are very far away from our straight line. There is no relation at all. R is equal to 0. No relation at all. Now come to next one. The graph is coming from up to down. It is negative. Negative relation is there. Here R value is -0.4 showing here. Means no, very rarely 1 or 2 points touches that line of regression. Other points will be far away from the line of regression. It is a completely negative relation. Now for that, let us see one example. They are asking find covariance for this data. Here 2 measurements are given, height, weight. Height is given in meters, 1.60 meters, 1.64 meters, 1.71 meters. Means they are 160 centimeters, 164 centimeters, 171 centimeters, like that. And their weight also given in kg, 53 kg, 57 kg, 60 kg, like that they had been given. For other sum also, directly they had given their height in centimeters, 160 centimeter, 164 centimeter, 171 centimeter. Their weight is given like that, 53 kg, 57 kg, 60 kg. Now they are asking covariance for this data, A and B. What is the covariance they are asking? For that, here S of xy, that is called covariance. Covariance from x to y. It is not as S of xy. It is nothing but sigma xy by n minus sigma y by n into sigma x by n. So using that formula, S of xy is becoming 1/3 into sigma xy will become 280.88 minus sigma y 170 by 3 into sigma x 4.95 by 3. Its value is 0.126. Like that, S of yx also we can find. It is also same formula, 1/3 into 280.88 minus sigma x by n into sigma y by n. So it is also becoming 12.6. So what is the significance? Significance is very high here. Here we can see that we get quite different values by measuring in pounds and inches or kg and feet, etc. They will all be positive, but their sizes will not convey useful information because meter is very much different than centimeter, and kg is very much different than pound. That's why this difference will come. That difference is in a high way or low way. That relation is nothing but correlation. Same like it. Let us see this example also. Here, one people, he got mass marks out of 30 like this. Some A to J peoples are there, students are there. Out of 30 in mathematics, they are getting 20, 23, 8, 29, 14, 11, 11, 20, 17, 17. Like that, the physics marks out of 40 are given like this: 30, 35, 21, 33, 33, 26, 22, 31, 33, 36, like that they are given. Now, now we are comparing their maths marks with physics marks. How well they did in maths, how well they did in physics, their performance in maths and physics, we are comparing here by finding their rank of correlation. So for mathematics, all the sigma xy is here 5313. So you use that in formula 1 by n into 1 by 10 into because these are 10 in number. From A to J students, there are 10 students in number. That's why 1 by 10 into 5313 minus 17 into 30 by S of x into S of y. So it will become S of y is equal to square root of 1 by n, means 1 by 10 into, we are using formula only, 3250 minus 17 square, it is root 16, root 36, its value is 6. Like that, S of y is also, it is becoming 5. So R is equal to, substitute these values in that, 531.3 minus 510 by 6 5s. So its value is 0.71. Like that, we are finding rank correlation. So in another way also, we can find using tabular form. Let us take the child in one column, A to L. Their years in years, take in one column. Their marks in and their test analysis, let them take in 5 minutes like this. Then here sigma x is becoming 108, sigma y is becoming 637.2, sigma x square is 1060.1, sigma y square is 339694.2, sigma xy is 56823.4. So using our correlation constant, and compare the values between x and y, access the statistical significance of our value and interpret our results like this. Now, using the formula S of xy is equal to what? 1 by n into sigma xy minus xy bar. Here x bar is equal to 108 by 12, it is 9. Y bar is equal to 6373 by 12, it is 531. Here x bar is 108 by 12, it is 9. Here y bar is 6372 by 12, it is 531. Same like that, S of xy 1 by n formula. So using that, it is becoming 2.7096. Like that, S of y, it is also becoming 33.4290. Now combine all these values, keep them and put it in our formula. R is equal to minus 43.55 by 2.7096 into 33.4290. It is minus 0.481. Here negative value has come. This negative value depicts negative correlation, means the value the relation goes from top to bottom. It means like that. So this indicates weak negative correlation. That is what we are telling now. This indicates weak negative correlation. But to apply a significance test, the null and alternative hypothesis need to be defined. H naught means it is in a test of hypothesis. We will know this terminology. H naught means it is a null hypothesis. Null hypothesis means in whatever in given sum, whatever actual statement is given, that we take it as null hypothesis H naught. In reverse to that, we will assume one more hypothesis. It is called alternate hypothesis. It is denoted by H1. H1 is called alternate hypothesis. So, if the z score value is less than 1.96, then we accept null hypothesis. Otherwise, we have to reject null hypothesis and we have to accept alternate hypothesis. That is the procedure. Here, H naught is a null hypothesis, H1 is alternate hypothesis. Here, almost all the sums we take significance level is 5%. 5% means it is a two-tailed test. Left-tailed test, right-tailed test. So, using the table of critical values in the appendix for n is equal to 12, R value is becoming plus or minus 0.576. So, that is the critical region where H naught is rejected is R is less than minus 0.576. If our calculated value is less than minus 0.576, then we have to reject that null hypothesis. So, and if R is greater than 0.576, then also we have to reject the null hypothesis. So, since R is equal to minus 0.481, there is insufficient evidence to reject the null hypothesis. Means then we have to keep that in a abysmal interval. Keep like that. Immediately we cannot tell it is rejected. Though here see what the significance of R. With only two pairs of values, it is unlikely that they will lie on the same horizontal or vertical line, giving a correlation coefficient of 0. But any other arrangement will produce value of R equal to plus or minus 1, depending on whether the line through them has a positive or negative gradient. Here, what is gradient? The slope is called gradient. Here, the slope of this line is denoted by M. That slope is inclined with how many degrees with x-axis, horizontal line. It is called actually gradient. So, there is a slight difference between slope and gradient. Gradient is sine angle of slope, actually. So, the straight line becomes much more significant whenever it is defined with a gradient. So, this table showing critical values at 5% significance level, almost so many sums on correlation and test of hypothesis, they will ask for to calculate at 5% significance level. So this table gives some indication of how likely some values of the correlation coefficient are. For example, for n is equal to 5, R value is some 0.878 rank. It means that there is only a 5% chance of getting a result of 0.878. It means like that. N is equal to 5. R is equal to 0.878 means there is only a 5% chance of getting a result of 0.878 or greater if there is no correlation between the variables. Such a value therefore indicates the likely existence of a relationship between the variables. Here, number of pairs are given and rank correlation are given. Suppose there are 3 number of pairs are there. Significantly, its rank correlation comes as 0.997. If it is 4, 0.950. If it is 5, 0.878. If it is 6, 0.811. If it is 7, 0.755. If it is 8, 0.707. If it is 9, 0.666. If it is 10, 0.632. So, these values randomly depicts for number of pairs. What will be the rank correlation? Now, let us see the more detailed tables of critical values are available for a range of significant levels and values of n. Their calculation relies on the data being drawn from joint normal distributions. So, using them in other circumstances cannot provide an accurate assessment of significance. Now, let us see first graph. Here, this correlation shows strong positive correlation because all those assumed values are very closer to each other. They are very, very nearer to each other. Whereas in second one is somewhere, other is somewhere, other is somewhere. They are far away from one another. It depicts weak positive correlation. And in third graph, there is no relation at all. That is why here this is for no correlation. Whereas fourth one, they are descending from top to bottom in irregular way. That's why it depicts strong negative correlation. Same like that, this depicts very weak negative correlation. So, let us see one interesting problem on this. Is there a linear relationship between the rankings produced by the two judges? Here, Spearman's rank, the two judges will follow the same procedure, but depending upon their intellectual estimation, slightly one may differ from other. Using Spearman's rank correlation coefficient answers this question by simply using the ranks as data and in the product moment correlation coefficient R and denoting it R1. Again, a scatter diagram. This is nothing but a scatter diagram. A scatter diagram may be drawn and the presence of the points plotted in are very near. The top right and bottom left areas indicates a positive correlation. Like that, here we can show Spearman's rank correlation coefficient using this diagram. Yes, how can we find Spearman's rank correlation coefficient? R is equal to 1 by n into sigma xy minus xy bar by sx into sy. Here, x bar and y bar are same here. It is 55 by 10. It is 5.5. Now let us calculate s of x. Here they both are same. S of x is equal to s of y is equal to sigma xy. It is 385 by 10 minus 5.5 whole square. So it is square root of 8.25. And let us find sigma xy. It is 2 into 6 into 2 into 6 plus 9 into 9 plus etc. 7 into 5. It is 362. From table, so we are finding this is sigma xy. Now let us keep the value in rank. Then it will become 1 by n into n, means 1 by 10 into 362 minus 5.5 square divided by square root of 8.25 into square root of 8.25 sx into sy. So it is becoming 0.721. Like that, we are finding Spearman's rank correlation. Now let us see one more sum. There are suppose the 10 students are there, or 10 cases are there from A to J. Judge 1 is giving them score like this. For A, he has given 2. For B, he has given 9. Like that for J, etc. For J, he has given 7. For the same incident, Judge 2 is giving score like this. 6, 9, 2, 1, 8, 4, 3, 10, 7, 5, like that he is giving. There is much variation between giving scores from Judge 1 to Judge 2. Now, let us take the difference. Their scores difference. 6 minus 2, 4. 9 minus 9, 0. Like that, take the difference and take their mod value, modulus of difference, and square it. So they are becoming 16, 0, 1, 4, 4, 0, 9, 4, 4, 4. Now, let us find sigma d square. Here their value sigma d square is becoming 46. Now, using a Spearman's rank correlation, R is equal to 1 minus 6 sigma d square by n into n square minus 1. Spearman's rank correlation. In this, we have to use all this. Sigma d square we found here. N value known to us. Accordingly, n square will come and simplify. Then the R value is becoming 1 minus 6 into 46 divided by 10 into n square. 10 square means 100 minus 1. So its value is 0.721 up to 3 decimal. So let us see what are limitations of correlation. So there are some limitations are there, some barriers are there for this in finding this correlation. Well, especially the first point is R is a measure of linear relationship only. It only gives the relationship linearly, but if it goes quadratically or whatever it may be cubically, that measure we cannot assume, we cannot find, we cannot estimate properly. This is only applicable for linear relationship. There may be an exact connection between the two variables, but if it is not a straight line, R is no help. It is well worth studying the scatter diagram carefully to see if a non-linear relationship may exist. Perhaps studying X and Y may provide an answer, but this is only one possibility. So the first limitation is for non-relationship, non-linear relationship, it doesn't hold. First limitation. Like that, correlation does not imply causality. So, correlation does not imply causality. A survey of people, a survey of pupils in a primary school may well show that there is a strong correlation between those with the biggest left feet and those who are best at a mental arithmetic. Like that, we can compare them using so many parameters. So, it is correlation does not imply causality. That is the second barrier. Correlation does not imply causality. Next, third one is an unusual or freak result may have a strong effect on the value of R. What value of R would you expect if point P were omitted in the scatter diagram opposite? So that is also one weak point here. Here, an unusual or freak result may have a strong effect. An unusual result may have strong effect. So these are the three main limitations or drawbacks of rank correlation. So we can analyze all this with the help of our known test of hypothesis or scatter diagrams. These are the scatter diagrams, and these are the Z values. So using this Z value or Z score, we can convert the data into this. So as a part of recapitulation, we can find rank correlation using the formula R is equal to n into sigma xy minus sigma x into sigma y whole divided by square root of n into sigma x square minus sigma x whole square into n into sigma y square minus sigma y whole square. So same like that, we can find the rank correlation using null hypothesis and using Spearman rank correlation. That is Spearman's rank correlation is rho is equal to 1 minus 6 sigma d square by n into n square minus 1. So using all this, we can analyze Spear rank correlation, and there are three drawbacks, limitations, shortcomings for correlation. They are for non-linear relationship, whatever discussed cannot hold, because if it is a measure here, R is a measure of purely linear relationship only. So for non-linear relationship, it doesn't hold. And second limitation is correlation does not imply causality here. And third drawback is an usual result may have strong effect here. Perhaps it may be very silly thing, strong thing, but while we are calculating relationship, it may give very strong effect. So sometimes it may not match to the actual situation. So these are the three shortcomings of a rank correlation. Thank you. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.